formula to calculate the expected voltage loss based on the length of cable run, size, and voltage used is voltage loss equals 2 times the length of cable run times the resistance of cable per unit length times the current, all divided by the voltage. In this formula, voltage loss is the expected voltage drop in volts. Length of cable run is the distance between the power source and the load in meters. Resistance of cable per unit length is the resistance of the cable per meter in ohms per meter. Current is the current flowing through the cable in amps. Voltage is the voltage of the power source in volts. Let's break down each component of the formula and how it affects voltage loss. Firstly, consider the length of the cable run. The longer the cable, the greater the voltage loss. This is because the resistance of the cable accumulates over its length. Imagine electrons flowing through a long pipe. The longer the pipe, the more friction they encounter, leading to a greater drop in pressure, which is analogous to voltage drop. Secondly, examine the resistance of the cable per unit length. This value depends on the material and size of the cable. Copper and aluminum are common conductor materials, with copper generally having lower resistance. The larger the cross-sectional area of the cable, the lower its resistance. Cable manufacturers typically provide resistance values per unit length, such as ohms per meter, in their data sheets. Thirdly, think about the current flowing through the cable. The higher the current, the greater the voltage loss. This relationship is described by Ohm's law, which states that voltage drop is equal to current times resistance. As current increases, so does the voltage drop across the cable's resistance. Fourthly, consider the source voltage. Voltage loss is inversely proportional to the source voltage. This means that for a given amount of power being transmitted, a higher voltage will result in lower current and therefore lower voltage loss. This is why high voltage transmission lines are used for long-distance power delivery. To apply this formula effectively, you need to ensure consistent units. If the length of the cable run is measured in feet, you need to convert it to meters by multiplying the length in feet by 0.3048, since 1 foot is equal to 0.3048 meters. Similarly, if the resistance of the cable is given in ohms per foot, you need to convert it to ohms per meter by dividing the resistance in ohms per foot by 0.3048. The current should always be in amps, and the voltage should always be in volts. Let's illustrate this with an example. Suppose you have a 120 volt circuit powering a load that draws 10 amps. The cable run is 50 meters long, and the cable has a resistance of 0.5 ohms per meter. Using the formula, the voltage loss would be 2 times 50 meters times 0.5 ohms per meter times 10 amps divided by 120 volts, which equals 0.417 volts. This means that the voltage at the load is 120 volts minus 0.417 volts, or 119,9583 volts. Now, let's consider another example using American wire gauge or AUG standards. Suppose you are using 12 AWG copper wire to supply a 20 amps load over a distance of 75 feet at 120 volts. First, convert the length to meters. 75 feet times 0.3048 meters per foot equals 22.86 meters. According to standard wire tables, 12 AWG copper wire has a resistance of approximately 6.52 ohms per 1000 feet at 20 degrees Celsius. Convert this to ohms per meter. 6.52 ohms per 1000 feet divided by 1000 feet equals 0.652 ohms per foot. 0.652 ohms per foot divided by 0.3048 meters per foot equals 0.214 ohms per meter. Now, apply the formula. Voltage loss equals 2 times 22.86 meters times 0.214 ohms per meter times 20 amps divided by 120 volts, which equals 0.1628 volts. Therefore, the voltage at the load is approximately 120 volts minus 0.1628 volts, or 119.8372 volts. It's important to note that the acceptable voltage loss varies depending on the application and relevant electrical codes. The National Electrical Code (NEC) typically recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. For sensitive electronic equipment, even smaller voltage drops may be necessary to ensure proper operation. If the calculated voltage loss exceeds the acceptable limit, you have several options to reduce it. Firstly, you can increase the size of the cable. A larger cable has a lower resistance, which reduces voltage drop. Secondly, you can shorten the length of the cable run if possible. Thirdly, you can increase the voltage of the power source, although this may require changes to the equipment and wiring. Fourthly, you can reduce the current flowing through the cable by using more energy-efficient equipment or distributing the load over multiple circuits. In addition to the basic voltage loss formula, there are other factors that can affect voltage drop in real-world installations. Firstly, temperature affects the resistance of conductors. As temperature increases, the resistance of the conductor also increases. This means that voltage loss will be higher at higher temperatures. The NEC provides temperature correction factors that can be used to adjust the resistance values in the formula. Secondly, inductive reactance can contribute to voltage drop in alternating current, or AC, circuits. Inductive reactance is caused by the magnetic fields generated by AC current flowing through conductors. The effect of inductive reactance is more pronounced in long cable runs and at higher frequencies. For most residential and commercial applications, the effect of inductive reactance is relatively small and can be ignored. However, for long cable runs or specialized applications, it may be necessary to include inductive reactance in the voltage drop calculation. The formula for voltage drop in AC circuits that includes inductive reactance is more complex and involves vector calculations. It typically requires the use of specialized software or calculators. Thirdly, connections and splices can add resistance to the circuit and contribute to voltage drop. It's important to use high-quality connectors and make sure that they are properly installed to minimize resistance. Loose or corroded connections can significantly increase voltage drop and even create a fire hazard. Fourthly, unbalanced loads in three-phase systems can cause voltage imbalances and increase voltage drop in some phases. It's important to balance the loads as much as possible to minimize voltage imbalances. Voltage imbalances can damage equipment and reduce its efficiency. The NEC provides guidelines for balancing loads in three-phase systems. When selecting cable sizes, it's important to consider not only voltage drop but also ampacity, which is the current carrying capacity of the cable. The ampacity of a cable depends on its size, insulation type, and installation conditions. The NEC provides ampacity tables that specify the maximum current that a cable can safely carry. It's important to choose a cable size that has sufficient ampacity for the expected load current. Overloading a cable can cause it to overheat and potentially start a fire. In summary, calculating voltage loss is an essential step in designing and installing electrical circuits. The voltage loss formula provides a simple and effective way to estimate voltage drop based on cable length, size, current, and voltage. By keeping voltage loss within acceptable limits, you can ensure that equipment operates properly and safely. Remember to consider all factors that can affect voltage drop, including temperature, inductive reactance, connections, and imbalanced loads. When selecting cable sizes, it's important to consider both voltage drop and ampacity. By following these guidelines, you can design and install electrical circuits that are both efficient and safe. Proper voltage drop calculations are crucial for several reasons. Firstly, voltage drop affects the performance of electrical equipment. If the voltage at the load is too low, the equipment may not operate correctly or may be damaged. For example, motors may run slower and overheat, lights may be dimmer, and electronic devices may malfunction. Secondly, excessive voltage drop can waste energy. When voltage is lost in the cable, that energy is dissipated as heat. This wasted energy increases the cost of electricity and reduces the overall efficiency of the electrical system. Thirdly, voltage drop can affect the safety of the electrical system. Excessive voltage drop can cause equipment to overheat and potentially start a fire. It can also cause nuisance tripping of circuit breakers, which can disrupt service and create safety hazards. To minimize voltage drop, it's important to choose the correct cable size for the application. The NEC provides guidelines for selecting cable sizes based on the load current, cable length, and allowable voltage drop. It's also important to use high-quality connectors and make sure that they are properly installed. Loose or corroded connections can significantly increase voltage drop and create a fire hazard. In addition to the NEC, other standards and guidelines may apply to voltage drop calculations. For example, the Institute of Electrical and Electronics Engineers, or IEE, publishes standards for power systems that include recommendations for voltage drop limits. These standards may be more stringent than the NEC requirements depending on the application. When designing electrical systems, it's important to consult all applicable standards and guidelines to ensure that voltage drop is within acceptable limits. There are several tools and resources available to help with voltage drop calculations. Firstly, there are online voltage drop calculators that can quickly and easily calculate voltage drop based on the input parameters. These calculators typically use the voltage loss formula and provide results in volts or as a percentage of the source voltage. Secondly, there are software programs that can perform more complex voltage drop calculations, including the effects of temperature, inductive reactance, and unbalanced loads. These programs are typically used by electrical engineers and designers for larger and more complex projects. Thirdly, cable manufacturers provide datasheets and specifications that include resistance and ampacity values for their cables. These datasheets are essential for accurate voltage drop calculations and cable selection. Fourthly, the NEC provides tables and examples that illustrate how to calculate voltage drop for various types of circuits and loads. These examples can be helpful for understanding the principles of voltage drop and applying the voltage loss formula correctly. In conclusion, voltage drop is an important consideration in electrical system design. By understanding the voltage loss formula and the factors that affect voltage drop, you can ensure that equipment operates properly and safely, energy is used efficiently, and the electrical system is reliable. Remember to consult all applicable standards and guidelines and use appropriate tools and resources to perform accurate voltage drop calculations. In practical applications, several factors can complicate voltage drop calculations. Firstly, the load may not be constant. For example, a motor may draw a higher current during startup than during normal operation. In these cases, it's important to consider the maximum load current when calculating voltage drop. Secondly, the cable may be installed in a conduit or raceway, which can affect its ampacity. The NEC provides directing factors that must be applied to the cable ampacity when it is installed in a conduit or raceway. Thirdly, the cable may be exposed to high temperatures, which can also affect its ampacity. The NEC provides temperature correction factors that must be applied to the cable ampacity when it is exposed to high temperatures. Fourthly, the cable may be subject to voltage harmonics, which can increase voltage drop. Voltage harmonics are caused by nonlinear loads, such as electronic devices, and can distort the voltage waveform. In these cases, it's important to use specialized equipment and techniques to mitigate the effects of voltage harmonics. To account for these factors, it's often necessary to use more sophisticated voltage drop calculation methods. These methods may involve the use of computer software or specialized instruments. It's also important to consult with a qualified electrical engineer or technician to ensure that the voltage drop calculations are accurate and that the electrical system is designed properly. In addition to the voltage loss formula, there are other methods for reducing voltage drop. Firstly, you can use a voltage regulator to maintain a constant voltage at the load. Voltage regulators are electronic devices that automatically adjust the voltage to compensate for voltage drop. Secondly, you can use a step-up transformer to increase the voltage at the source and then a step-down transformer to reduce the voltage at the load. This method is often used for long cable runs where the voltage drop would otherwise be excessive. Thirdly, you can use a dedicated circuit for each load. This method reduces the current in each circuit and therefore reduces voltage drop. Fourthly, you can use a ground rod to provide a low resistance path for ground fault currents. This method helps to prevent voltage drop during ground fault conditions. By implementing these methods, you can minimize voltage drop and ensure that equipment operates properly and safely.